Hello everyone, this is Professor Keen. We have been talking about Newton's Principia, Book 1. We just talked about his definitions, his scholium on absolute and relative motion, then we talked about his axioms or his three laws of motion, and then we started talking about the corollaries or consequences of Newton's three laws of motion. I'd like to pause at this point before we make our way into chapter 23 to talk a bit more about free body or force diagrams. I introduced these to you in the context of doing our force and rotation lab, but I'd like to go back to this topic and explain it to you once again and spend some time going through some example problems because we really need to master the use of free body or force diagrams. So that's the topic of this lecture and probably my next 3 or 4 lectures. Okay, so free body or force diagrams and how to use them. So what do we mean by a free body or a force diagram? A free body diagram is really a simple drawing that describes all of the forces that are acting on a particular body. Okay, so for example, to describe the force acting on a book that is lying on a table, we can represent the book by a simple dot. So it's a schematic, kind of a cartoon. We represent the book by a dot, and then we draw one arrow for each force that is acting on the book. These arrows begin on the dot and point in the direction that that force is acting. It's very important to only draw forces in a free body diagram. I think sometimes people have a temptation to draw arrows representing momenta or velocities or other kinds of things, but a free body diagram, technically speaking, only includes arrows represent forces, which act on the body. So that's another thing I'd like to emphasize, not only that you should only have forces in a free body diagram, but only the forces that are directly acting on that body. So there may be all kinds of forces involved in some complicated situation with many interacting bodies, but for a particular body, you only draw forces that are acting on that body. Okay? So, for example, let's suppose we have a book. Okay, so here's a picture of a book. Okay, and here are the pages of the book. And this book, let's suppose, is resting on the surface of a table. Okay, so this is example number 1. And let's suppose we wanted to draw a free body diagram for the book. Okay, so that is the object that I want to draw a free body diagram for. Okay, so like I said, what you do is you first draw a dot that schematically represents the book, and then we draw an arrow that begins on the dot and points in the direction of each force acting on the book. So the first force that I'm going to draw is the force of gravity. Maybe we'll call this W for the weight of the book. Okay, this is the force with which the earth pulls down on the book, also called the weight of the book. Okay, that's one force acting on it. And then the other force, well, that's not the only force acting on the book. The table is going to be pushing up on that book. So I'm going to draw another arrow. Whenever you have a surface pushing on an object in a perpendicular direction to the surface, that is called a normal force. So it's very common to write this as an N. That is the table pushing up on the book. And again, this is called a normal force. Not normal in the sense that it's regular, but normal in the sense that it's perpendicular to the surface of the book. So I'll make that comment, I'll emphasize that right now. Whenever you have what's called a normal force, the normal force is a force acting on an object by a surface that is perpendicular to the surface. So the force is perpendicular to the surface. This we're going to distinguish later on between a normal force and a friction force. So a friction force is another kind of force that a surface exerts on something else, but that friction force is going to be tangential to the surface. The normal force is perpendicular to the surface. Okay? All right, so that's a simple example of a free body diagram. This dot represents the book. That's one force, and that's another force. This is the free body diagram for that book. Okay? Now, of course, there are going to be other forces we could consider. The book is also pushing on the table, but that would be a separate free body diagram. Notice that both of these forces are acting on the book. On the book. These are forces that are trying to push on the book. Okay? Let's do another example. Example 2. Consider two books. Consider two books. A 100-gram book, 100-gram book that is resting atop a 1,000-gram or 1 kilogram book that is itself resting atop a table. So this is a little bit more complicated. And I want you to draw, or I'm going to show you how to draw free body diagrams for each book. And I want you to identify, or I will show you how to identify the magnitude or the size of each force in the free body diagrams. Okay, so I'm just going to draw this, not schematically, but actually draw the situation here. So we've got, here's our small book. This is our 100-gram book. Okay, and this is going to be resting on top of this larger book, the 1,000-gram or 1 kilogram book. And that book is going to be resting on the surface of this table. Okay, so I'll call this one the little mass. It's 100 grams. And this one is the big mass, I'll write a capital M, for 1,000 grams. Okay, now we want to draw a free body diagram for each of these. So we know we have two objects, so we will need to draw two free body diagrams. Okay, so I'm going to indicate this one is the free body diagram for the little mass, and this is the free body diagram for the big mass. I'm putting these there just to indicate that those are two separate free body diagrams. Okay, so let's start out by asking, what are the forces acting on this small book? Well, the first force, we'll start with this one. That's the weight of the book itself, the weight of the little mass. Okay, and I'll write in English what this is supposed to mean. This is the gravitational force of the Earth pulling on the little mass. Okay, the Earth pulling on the book. And then, that's not the only force acting on this. There's also another force acting on it. We'll call this N1. That's a normal force because the surface of the book is pushing perpendicularly upward on this book. So this is the big book pushing up on our little book M, right? So notice that both of these forces are acting on that mass. That means it's appropriate for you to include both of those arrows in this free body diagram. Okay, and by the way, we can tell right away what the size of this weight is going to be, we can multiply this mass times g. Actually, it would be 0.1 kilograms times g, which is about 10 meters per second squared. And so this is going to end up being a 1 Newton force. Okay, we'll come back to that in a minute. Let's finish drawing the free body diagrams first. All right, those are the only two forces acting on the small book. What about on the big book? Well, on the big book, once again, we're going to have this force. That's the weight of the big mass. That is the Earth pulling on the big book, that big mass. Okay, that's one force. There's another force. That is the force that the table is pushing up on that. So I'm going to call that, I don't know, what do I want to call that? N2 is the table pushing up on this big mass. Okay, and that's not those are not the only two forces acting on this book. There's also another force of this little book pushing down on the big book. Okay, so I'll draw another arrow. I'm going to draw this off to the side a little bit. And this I'll call N3 because once again, it's a normal force. It's a force with which the surface of the little book pushes downward on the big book. So this is the small book pushing on the big book. Okay, so notice all three of these forces are acting on that mass, and that's why I've included all three of those forces in the free body diagram for that mass. Okay, so those are the three forces acting on. Notice there are only two forces acting on the little book, and there are three forces acting on the big book. Okay, now what are the sizes of these? Let's start with this one right here. I'm going to say step 1. I know immediately how big this force is. This force is going to be equal to mass times g. G, you can think about that as a conversion factor between mass and weight. It's 10. So here we have 0.1 kilograms times g is 10. I'm rounding 9.8 to 10 meters per second squared. And the units of kilogram meter per second squared is newtons. So there'd be a 1 Newton force pulling down on this little book. Okay? What about this force N1 right here? Well, this is step 2. We can figure this out right away. So let me say this is what step we're doing in figuring this out. So these are the steps. Okay. Right. So what's this force? It's tempting for people to say, well, Newton's third law says for every force there's an equal and opposite force, and those two are equal and opposite forces in the sense of Newton's third law, so that one must be 1 Newton also. Well, you're correct that N1 is 1 Newton, just like that, but it is not because of Newton's third law. These are not equal and opposite forces in the sense of Newton's third law, as I mentioned before. And we know that because they're both acting on the same object. Whenever we're talking about Newton's third law, we're talking about two objects interacting, and the equal and opposite forces that Newton's talking about in that are acting on different bodies. These are both acting on the same body, so those are not the equal and opposite forces that Newton is talking about. Okay? They do happen to be equal in size and opposite in direction, but we know that by Newton's second law. We know that because this book is not accelerating, the sum of these forces must be 0. So by Newton's second law, the sum of all the forces acting on it must be 0 so that the acceleration is 0. So we know that N1 should be equal in size to the weight of the book by Newton's second law, which means that N1 should also be 1 Newton. So it's the same force and it's in opposite direction so that this object does not accelerate up or down. It's sitting still, it's static. Okay? So the weight is 1 Newton. The normal force with which the big book pushes up on the little book is 1 Newton so as to support it and keep it from falling. Okay? If, of course, we got rid of it, if we evaporated the table and burned up the book, suddenly this book would fall. That's because the weight didn't go away, but the normal force would go away, and this unbalanced force then would cause it to accelerate downward. Okay, now let's go on to the free body diagram for the lower one. Well, we know this is step 3. This is an easy one to do right away. We can figure out the weight of the big book. The weight of this big mass is going to be its mass, capital M times G, and that's 1 kilogram times 10 meters per second squared, so that's going to be 10 newtons is going to be that force, right? All right, do we know any of these other ones? Well, we do know this one. This will be step 4. Okay, step 4, we know that N3, that is the force that the small book is pushing down on the big book. That one we can deduce from Newton's third law, because the force with which the big book is pushing up on the little book has to be equal and opposite to the force with which the little book is pushing down on the big book, right? So this pair, N1 and N3, are the equal and opposite forces that Newton is talking about in his third law. Object 1 pushes on object 2 with a normal force. Object 2 pushes on object 1 with a normal force. Those two are equal and opposite forces. That is that N3 must be equal to N1 in size by Newton's third law. So that means that N3 has to be equal to 1 Newton. Okay, so we know N3 is 1 Newton. I hope you're not confused by the N here. That's not a normal force, that's a Newton. We know the weight of the little book is 1 Newton. We know N1, that's the force with which the big book pushes up on little book, is 1 Newton. We know the weight of the big book is 10 newtons. And now the only one we need to find out is N2, the force of the table pushing up on this mass. That would be step 5. Well, by now, Newton's second law, we know that because this mass is not accelerating, the sum of all these forces, Wm, N3, and N2, must all balance each other. That is, N2 must be exactly equal to the sum of these two downward forces. Otherwise, the book would fall, and it's sitting still. It's not accelerating, so that means 10 Newton plus 1 Newton, which is 11 newtons downward, has to be balanced by the table pushing up on it. So that means that N2 must be equal to 11 newtons. So the table is pushing up on that book with a force of 11 newtons. Okay, there, we have completely figured out all of the forces acting on these two books. We've drawn free body diagrams, and we've used Newton's second law and Newton's third law and the relationship between mass and weight to solve for all of the forces. And we will stop there.